we annotated the dataset for PII, and then we trained and named the entity recognition model on it. And we used this model that we call StarPII to detect like personal information in the whole training data set, and then we removed it. The last step is the data decontamination, because you don't want to train on a test set that you're gonna evaluate on later and have data leakage. So we removed like the ones that we evaluated on, like human eval, multi-PLE, and DS1000, and other benchmarks. You can find like more details in the paper. And also the code for the whole data preprocessing, near duplication, PI removal, and everything is available on GitHub and BigCode Project. That was it. Now I will tell you about like some special formats we introduced in the dataset. So for code, we add prepended some tokens and some metadata at the beginning of each file. So we added the repo name, the file name, and the GitHub stars. And yeah, we're hoping that this would come in handy later if you want to condition on this metadata. And you will see later that the file name metadata, for example, came in very handy during the evaluation. For GitHub issues, we also wanted to separate them from the normal code because they are conversations. So we use tokens like issue start, issue commit, and issue closed to separate like the events inside the conversation. We did the same for Git commits. So we basically have the file before the commit and after the commit with the text message, and we use these tokens to separate them. And during inference, we found that we can use this format to ask the model to modify code or to fix a bug. You just give commit before, and then you give the function. For example, here, def for Fibonacci, you write as a message, add type hints to the function, and then the model outputs the function with the type hints. There's also some ongoing work for fine-tuning Git commit to improve the performance on this specific task. The last data source we had is Jupyter Notebooks. So this is for the structured notebooks where we separated code columns from markdown columns from outputs. So we basically have like Jupyter text, and then you have the markdown and Jupyter code, and then the code, and then the outputs. And during inference, we found that you can still use these tokens to make the model predict the outputs. For example, here the model input like is a list, and then you have prints, the double of the elements that are in the list. If you put Jupyter output, it gives you the list where each element is like its double. So yeah, this formatting worked during the pre-train. We added this, and we can also do it during inference. So that was it for the data part. Now let's move to the architecture. Everything I'm going to present is already available in our Megatron code base that we use for training, and the final model architecture is integrated in under BigCode. So we did a lot of architecture choices, and they all came from the answer to a simple question. What do people want from a code model? The first thing is fast inference, because one of the main applications of these models is to integrate them into an IDE, for example, like a VS Code extension. So you want to have a very low latency, otherwise the user experience would be very bad. You also want to be able to do cheap generations, especially when you have a large batch and you have long sequences. This requires a lot of memory. So especially and also in evaluation, we do that a lot for code models. We have to generate like thousands of solutions to problems, for example, in human eval, and then we have to execute them. So the models need to be able to process large batches fast. Another important thing, which is missing from many code models that were released before, is long context. For example, if you were to use this model, let's say in a VS Code extension, one potential improvement is instead of only feeding the model the current context of your file, you would also feed context from other files that are in the same repository. And if we were to do that, that would mean more text, and more text means more tokens. So you need to be able to fit a large context length into your model. One last thing is bidirectional context, which is a very common use case for code models. Let's say you have a block of code and you don't want it to just complete your code. You want to change something that is in the middle. And you can do that out of the box without decoder models because they are autoregressive. So yeah, we had to find an architecture choice that would enable all of these features. And so here's the answer to each feature. For fast inference, we have a 15 billion parameter model. You may say, why isn't it smaller? It could also be larger because you have to trade off performance for size. But we did a lot of code optimizations in the architecture that we integrated. We also released in the model, we're serving it through an API that uses text generation inference, which is a library that really optimizes the inference for large language models. And to have cheap generations, especially for large batches and sequences, we used multi-query attention, which really reduced the memory, and you can process much larger batches and really faster. And the idea of multi-query attention, or MQA, is that in the transformer block, you have different attention heads. And the standard way is to have like a different key and value for each head. And what multi-query attention does is that you have shared keys and values. And this really reduces the memory footprint because you have much smaller tensors, and you would need to load the smaller tensors from the memory during the incremental decoding. And this really helps with the generations. So this is for cheap generations. For the long context, so the SantaCoder model we released previously, for example, had 2,000 tokens context. And now we went for 8,000 tokens context. And since we know that flash attention is quadratic in sequence length, we can just go to 8 tokens with the same architecture that we had. So we used flash attention, which is an attention which is IO aware, and you can easily scale to 8 tokens context while having fast inference and also training. For the last part, which is bidirectional context, we use the fill in the middle train objective. It's basically, you don't change your loss, you just apply data transformation, where you take your file and you split it to 3, you have a prefix, suffix in middle, and then you swap them so that the model can learn to see a prefix and a suffix and then predict the middle that would go inside. So it's very easy to apply. And these are the different architecture choices we made, which make StarCoder very different from some other, not just code models, but also language models that are out there in the market. Yeah, so that was it for the architecture. For the training, the model was trained for 24 days on 512 GPUs. We used 4 tensor parallelism and pipeline parallelism, leaving us with 32 data parallelism. And the batch size was 4 million tokens, and we trained for 1 trillion tokens. So although the training dataset was around 300 billion tokens, we did multiple epochs, and the loss just kept going down, the training loss and also the validation loss. And we did the training in Gatron. So it was kind of a smooth sailing. We only had to restart the job once, I think, and the 2 other restarts were automatic. And everyone happily watched the loss go down. So now let's go back to the models we released. So we have 2 models, StarCoder base, which is the original model that's trained on 1 trillion tokens on more than 80 programming languages. And then we have StarCoder, which is basically just StarCoder based, fine-tuned on 35 billion Python tokens. These are the same Python tokens that we used during the pre-training. And we found that it's really improved performance on Python, but also on other programming languages, as I'm about to show you in the evaluation section. So first, one of the most popular programming languages is Human Eval. Whenever someone releases the model, this is the first table you see. So here I have the results for Human Eval in MVPP. And you can see that StarCoder base already outperforms much larger models like Palm and Llama and Lambda, and also CodeGen, which is like the largest open source code model that was there before StarCoder. And then after fine-tuning on Python, we did StarCoder, and StarCoder outperforms also CodeCushman. And a last result that we have is StarCoder prompted. So what is this model? This model is basically just StarCoder. And then when we evaluate on Human Eval, we change the prompt slightly. Because when we looked at the human eval generations, so human eval is basically you have a function signature and you have a docstring, and the model has to complete it. And then you take this function and you run it against unit tests. And if it passes, then good. If it doesn't pass, then it fails. And then you compute an average score called pass at one. When we looked at the model completions for some functions, we found that sometimes the solution was empty. The model would just put a hashtag solution here or to do for implement solutions. So it didn't even try to solve the problem. It was just putting these phrases. And so we tried adding the file name token that we conditioned on during the pre-training that says solution1.py, like if this was a solution to a problem, because often these solutions are correctly implemented. So the model is conditioned on this metadata. It's more likely to produce a more correct solution than just telling you pass or implement a solution. We also added like a comment. Here is the correct implementation of the code exercise. And this significantly boosted performance. We can go from 33 to 40% pass at one just because we have less of these automated failure cases. And we also tried this prompt on StarCoder base and CodeGen mono, and we didn't observe like a significant improvement. This only happens for StarCoder, which was further fine-tuned on Python. So these are the results on human eval, but we did a really extensive evaluation on other benchmarks and other programming languages. For example, MultiPLE, which is basically the translation of human eval to 18 other programming languages. And here I have Code Cushman 01, StarCoder, and StarCoder base. And the best model is highlighted in bold. And you can see that StarCoder and StarCoder base outperform all open access models. They're very competitive with Code Cushman. And we can see strong performance after the fine-tuning. So going from StarCoder base to StarCoder, well, there are some large differences in some programming languages that like Swift, where it got so much better. It went from 16 to 22. For other programming languages like Ruby, it was the opposite way. It's like it forgot Ruby at all. But overall, like StarCoder is also better in some programming languages and a strong multilingual model, which is good, meaning that you can still fine-tune and not lose performance in other languages. If anything, you might gain it. Another benchmark we evaluated on is DS1000, because human eval only has 164 problems, and they are kind of basic. DS1000, on the other hand, has 1,000 problems, like the name says. And it is like data science problems that are extracted from Stack Overflow and that were rewritten by the authors. And it's a bit more complex than human eval. And we can see that both StarCoder and StarCoder base are so much better than the other models. And the gap is much more significant than it was for human eval. So this is a table that shows the performance on the 7 libraries in the S1000. You can see that StarCoder base have competitive edge. And so the S1000 has 2 modes: completion, which is left to right, and then it has insertion, which is fill in the middle, where you have to solve the solution inside. And insertion seems to be even, completion, sorry, seems to be even better for StarCoder than for StarCoder base. Yeah. One last thing we evaluated on, and when we got the results, we were just as shocked as Pikachu here, is the reasoning tasks. So we tried prompting StarCoder. We added a series of dialogues in the context, as I'm about to show you later, and we saw that it can act as a tech assistant. It can really talk, it can reason. And that was surprising because it's a code model. But again, we trained on a lot of Markdown, a lot of HTML, and GitHub issues, which are conversations. And this seems to help with the text parts and conversational parts. But also when evaluating on the Helm reasoning tasks, the model outperforms much larger language models like OPT and also some Cohere models. So here, like the red one shows where StarCoder is positioned on the Helm list. And if you go to Helm, like there are 60 models, and StarCoder was really on the top, in the top 10 to 20 models on these tasks. And this suggests like having some reasoning abilities just from training on code. And I think there are some recent papers who are also trying to study that. So yeah, let me go back for prompt in StarCoder, where we were struck by the conversational ability. So Anthropic has the prompt called HHH, and it's basically a series of dialogues between a human and an assistant. And if you add it to the context, then the model can continue talking as if it were the assistant. And we did the same with the prompt called the TA prompt, technical assistant, sorry. So here is a snippet. You basically have first a prefix telling the model that it is an AI assistant and that it has to help the human in the requests as long as they are related to programming. And then you have a human that asks a question and then the assistant replies. So when we did that, we added it to the context, thanks to the 8K context length that allowed us to feed this prompt, which was 1,000 tokens. So we can't really do that with models that don't have a large context length. And if you ask it, for example, can you give me Python code that tells me weather in Bern, it does give a correct implementation. So this is without any instruction tuning. So of course, it's worse than other models that are instruction tuned. But just being able to have that with a simple prompt was very astonishing. Yeah, one last thing I'm going to compare to is Code T5+, which was released today. It's a new family of open encoder and decoder code models, which is cool. It can unlock some use cases, not just for code generation, but for example, for retrieval. So Code T5+ 16b is a bit behind StarCoder and StarCoder prompted, but they have an instruction-tuned version that they trained on Code Alpaca, which is basically output from Code DaVinci. It seems to give a good performance boost. They have 35 human eval, but still a bit behind StarCoder prompted. Now I'm gonna go to some other tools that we released with BigCode models and datasets. The first one is a VS Code extension. So there's a VS Code extension that serves StarCoder that you can download from the Visual Studio Marketplace. And it has autocomplete features that also use fill in the middle. And one cool feature it has is the membership test, because we trained our code model only on permissive data. But even when training on permissive, you still need to do code attribution. Instead, in case the model copies some code from the training data and spits it verbatim. So we have a membership test that checks whether what the model outputs is exactly taken from the training data. And this is in the VS Code extension. So if this happens, it tells you that this code was copied, and then you can go to a tool called Stack Search, where you can find the origin of the code, like what is the original author, what is the original license, and the repository on GitHub. Another thing that was released, not really in BigCode, but from the HuggingFace H4 team, is they fine-tuned StarCoder on an instruction dataset, the Open Assistant datasets in the Dolly. And they got an instruction StarChat that you can play with in StarChat Playground. Finally, we're releasing this model under CodeML OpenRail MV1, which is royalty-free. It also enables downstream distribution of derivatives. It includes some ethical use restrictions. And it is an improved version of the OpenRail license that makes it easier to use the model for commercialization. You can find the full agreements on this link. So that was my presentation. Thanks a lot for attending, and feel free to ask questions.
All right, awesome. Thank you for walking us through that. So much good stuff in the paper, and that was a great summary to it. So let's go ahead and look at the Slido to start off with some questions. Let's start off maybe with the initial item you talked about, which was PII. So why did you think to add a PII removal model? What was the intuition, and maybe what were some surprising results as you were going through that model development or cleaning phase?
Yeah, of course. Yeah, so this is like one of the important things to do with these models. If you train on personal information from people, it might be possible that it will output it. And serious efforts must be taken to try to mask it. So in the first iteration, we used regexes, and they were okay to detect IP addresses and emails, but when it came to passwords, secret keys, they were not really as good, even for some tools that are very popular on GitHub, which is why we decided to actually annotate our own data set, where we have human annotators like find PII in the data, and then we train the model. One thing we're worried about is how to scale this, because we had 800 gigabytes of data and you want to run a model on GPUs on all this data. But in the end, we optimized the inference, and it took, I think, it might seem a lot, but it could be worse. I think 800 GPU hours on A100s. Yeah, but we were able to have a much better performance than the regexes would. And playing with the model, it doesn't seem like it can spit PII out of the box, but there are definitely a lot of shortcomings. The model is not perfect. It could be improved. So at least we do our best to try to fix that.
Okay, awesome. And for PII, were there mainly mistakes made from people's repos, or was it based on the comments, since you trained on the GitHub conversations too?
Yeah, so looking at, sometimes they can be names in the licenses, so they are not mistakes, people are putting them there, but sometimes there are a lot of secrets and passwords, which are mistakes. So GitHub, I think it already detects if you have a secret, it can send you an email, but there's still action required from the user for that secret to be removed. So it's not always the case. So yeah, it could be a mistake. It could also be, for example, you have IP addresses that are there. People don't think they are like that crucial to remove, but we don't want our model to memorize it. So yeah, it's sometimes both. Sometimes it's voluntarily, but it doesn't mean that these people want you to train a model on these informations.
For sure. Yeah, I mean, we get another probably example of how many password 123s or other items are in there. Okay, great. So that was a PII general topic. Just looking through the next set of questions, maybe we can talk a little bit about the makeup of why you decided to include metadata, the conversations. Were you trying to experiment with the other sort of properties of being conversational, or did you just think that it would be useful for code generation?
Yeah, so yeah, the question is like why we added metadata for GitHub issues.
Yeah,
yes,
exactly.
Yeah, so like mainly because it's like conversations and not really code. So we didn't want the model like you have a comment and then it answers in an issue, or it was mainly a motivation to try to separate them, but also to have this conversation mode where you just put issue start and you say something and the model knows that it has to switch to conversation mode and it answers you with like, oh, hello, you want to fix this issue. And we did try it and it seemed also to work. But in general, if you try to prompt the model, hey, can you fix this? It immediately knows that it has to go to issues mode, even if you didn't put the token. So yeah.
Great, that makes sense. I think a big thing that people are interested in is pre-training and fine-tuning. So talk a little bit about StarCoder base and then StarCoder. So sort of why did you decide to release the base and the fine-tuned version? Maybe you can walk us through a little bit of the team's thinking process there, and maybe why did you choose that size of data set for the fine-tuning?
Yeah, of course. That's a good question. So we trained StarCoder base on multiple programming languages. And for example, if you see the CodeGen paper, they started with pre-training. They have CodeGen Multi, which is trained on multiple programming languages. But then they fine-tuned on an internal dataset of Python they had to have CodeGen Mono, which is much better as Python. So we also wanted to test that. Can we get like better performance, squeeze more out of the model if we fine-tune more on Python? Because I think that's the language that most people, for example, in data science care about. So, but we didn't have another Python data set, or the permissive one that we released is in the stack. So we just repeated data from what we already had. We tried one epoch, but it didn't seem to help. But going to two epochs, which is the 35 billion that we used, seems to help and manage to give us like much better performance, not just as Python, but also on other programming languages. And I think maybe going beyond two epochs would be too much because we already did 5 or 6 in pre-training and then 2 in fine-tuning. That's probably enough repeating data.
For sure. There were some questions about training objectives. Did you try to mix up the training objectives? I know you used the masked objective for the bidirectional one, but any other objectives you tried or wanted to try for fine-tuning versus pre-training?
Yeah, so like the bidirectional one, it doesn't really use masking, it's just the fill in the middle, which can allow you to have kind of the right context just because you swap the order during your data transformation. So it's like applied to half of the data set where you have the prefix and then the suffix and then the middle. For the rest, you just have the normal order. So yeah, that's the change we did. We were sticking to a decoder model, so we didn't really try other pre-trained objectives. There were some experiments going on. We tried UL2, but didn't manage to get good performance like we did with just the decoder model. We to this architecture.
Okay, makes sense. And I guess for some of the pre-training objectives, you removed quite a few languages out from the data set. I think you had 50 languages in there. Was there a reason for that? Sort of beyond just reducing the scope?
Yeah, so we had 350 programming languages and we kept 86. It was a matter of quality. We removed programming languages that had less than 500 megabytes. So it would just be noise if you add languages with 10 or 20 files. So I think we lost a lot of programming languages with this filter. And then the other one is to really try to keep a set of languages that are still supported, used by the community, that are not configs. And so, yeah, we had some people who, like, from research labs where they know multiple programming languages. It was a community effort. If people cared about programming languages, they said, could we add this? But yeah, we tried to keep the languages that had some data we could train on that were still used. There was a mistake. We excluded Swift. It was a human mistake. And then D, I think it was also removed, but because there was some misclassification. For the rest, it was a voluntary choice.
Okay, makes sense. And looking at the plots there, it looked like the more data that you added, the better the models generally got. Is that something you're looking to do in the future, is go beyond the 1 trillion data size, or do you think that that's a reasonable size to stick with?
Yeah, I think more data is always better, but the question is, where would you get more data? So now we could like do multiple epochs to reach the 1 trillion tokens, but maybe it could be interesting to explore adding more text, like natural language data, to the code one. So yeah.
Okay, awesome. Then we had some questions on fine-tuning here. So about languages or formats that are, I guess, not included in the training set. So do you think that's something, if an open source user wanted to do that, what would you recommend for them to do? Let's say that they had some SQL in there, or a specific variant of SQL, or some other querying language. Is it just as simple as fine-tuning it, or would you recommend something else?
Yeah, so I think, yeah, we already have like a very large set of languages, so it's very likely that the other we want to add is very similar to one that's already in the pre-training. So I think, yeah, the fine-tuning is definitely the way to go. Maybe tried with Python, it seemed to work, so you could also try it on another language. Something other people are like now trying is to have like a prompt where you kind of try to teach the model to a new language just by giving like some, for example, here's the implementation in SQL, here's the implementation in another language. It seemed to give like some results. I think fine-tuning would definitely give better results. We have some code for fine-tuning in GitHub repo for StarCoder, so that could be a good starting point.
Okay, awesome. And I guess this model, for people wanting to run it themselves, let's say that they want to deploy it within a large enterprise and there's some security considerations, do you have any recommendations on that, or should they just go to the HuggingFace website and run it out of the box?
Yeah, I mean, for people who want to host the model themselves, so the weights are open access, they can use them, and we also, the library that we're using to serve them in the API endpoint from HuggingFace is also open source. It's called text generation inference. So if they have the GPUs to deploy them, that would give them a lot of speed ups because it's highly optimized. Otherwise, if they don't have the GPU to host them themselves, the easiest would be to call the API endpoint from the HuggingFace model.
Awesome. And for the Visual Studio Code extension that you showed, is that also possible to fork and run locally, or can you point it to your own instance of the model?
So yeah, you can use the extension as it is if you want to use just StarCoder. If you want to fork it and maybe change the model, change something, it's also open source. I think if you go to the marketplace, you can find the link to GitHub. So yeah, that's totally possible.
Okay, awesome. Maybe a question on some of the test cases. So for generating sort of when you do programming, there's various stages, right? So you talked a little bit about using Jupyter notebooks and training on that data. Talked a little bit of the evaluation methods on writing test cases. So were there any other sort of hypotheses that you wanted to test regarding test case generation, or in general going through the development workflow, maybe like comment to some general structural code, then writing test cases, or vice versa? So maybe you can talk us through as a developer and data scientist, anything that you thought through on that regard.
Yeah, sure. So for example, yeah, one approach that came to my mind now, there was reading the Codify paper is like CodeT, where the model you force the model to generate not just a solution, but also unit tests. Then you do some averaging to kind of assume what solutions would pass. One other thing would be to try to do some solutions ranking. There were some methods to do that in alpha code that would also be interesting to explore, especially because we have multi-query attention. We can generate a lot of samples like in a large batch fast. So that's one thing that could be leveraged to try to rank the solutions and see which ones are better. Because now the pass at one is 30 to 40%, which means that it could fail 60% of the time. So yeah, exploring these would definitely be something worth giving it a try. Does that answer the question?
Yeah, I think that makes sense. So maybe to wrap up the public Q&A portion that's recorded, what's next? What's next for StarCoder? What are you interested in? Maybe talk a little bit, some things that maybe were left untouched in this paper release and model release, of course, of the things that you can right now.
Yeah, of course. Yeah, I think like BigCode, it was really nice because you can see how different people from different backgrounds could collaborate to put something to the community, and also while doing this responsibly. So yeah, we're very proud of what we were able to achieve. And I think for what's next, we're still under discussions if we would have another iteration. Would definitely be interested in exploring maybe other objectives, including more data of a different type, not necessarily code. So yeah, it's still to be defined.
Amazing. Well, thanks everybody for joining this. I'll stop the recording and the live stream, but thanks so much, Loubna, for sharing the presentation and answering the questions. We'll go into our private question session and after party now. So we'll see you next time, and thanks for watching the recording.
Thanks, everyone.
All right.
Thank you, Loubna. That's fantastic.
Sure. Thanks.
All right. So thanks everybody for joining the